This is a continuation of the atomic history. We know about Dalton now, who reproposed the idea of an indivisible atom. Okay, we're going to continue beyond that and discover our subatomic particles. Okay. As I go through it, the main things you want to take note of is the experiment that the scientists conducted, okay, the scientist's name, who it was that did the experiment, what were the results of the experiment, and how those results actually affected our atomic model. Okay, so we're starting with an indivisible particle, and we're going to get to our idea of the modern model of the atom. This is the evolution of how that happened. Okay, so here is our first subatomic particle.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might the parody Shakespeare say, "My use is great because I am so small."
The electron was the first discovery of a fundamental particle, and it is interesting to realize that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong.
So our first subatomic particle is the electron, and what's so crazy to think about is this is the first one discovered. Okay, yet all of our experimentation on the structure of the atom is still focused on the electron. Okay, it's our smallest piece of this. It's our smallest subatomic particle, but it's also the one that does everything. Right, it's the farthest out. It does the bonding. It does the reacting. It gives it a lot of its properties. So it's still the one that we study, even though it was the first one discovered. And again, he discovered it through using these cathode ray tubes. Just so you know, he showed his kit in the video, but a cathode ray used to be used a lot. People knew a lot about them. They were in old television sets. You know those television sets that are really, really deep? They've got a big black back to them. That's because they housed cathode rays, and how the image was actually projected onto the screen were these beams of electrons. And when they turned those dials to try to tune in the show, they were actually bending those rays, okay, changing the electrical field on the rays to make the picture become more clear. So old TVs, old computers, this was the technology that was utilized to produce an image. Okay, it's absolutely incredible. So that's Thomson's experiment. His model is frequently called the plum pudding model or the cookie model. The idea that there's this background ingredient that is positively charged and that there are negative chips in them as well. You can see already that they understand that there's a positive and a negative component, and that's because we know the atom itself is not charged. It's neutral. If it weren't neutral, everything you touch would react with you and give you an electric shock. Okay, electric shock is electricity, which is moving electrons. If everything were charged, you would always be getting charge into your body, and we knew that wasn't true. So if he found a charged particle, he knew there had to be a counter particle to valence it. Okay, let's look at what the next particle discovered was.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil. See what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
So Rutherford discovered the nucleus. And if you think about our picture of our atom, okay, Dalton had an indivisible atom. Thomson then kind of had a chocolate chip cookie with electrons embedded in some kind of positive dough. Rutherford all of a sudden has a nucleus. Okay? And Rutherford's picture of the atom is almost what we use today. The discovery of the nucleus was the most important discovery, in my opinion, of the atomic model. And the idea that there is some kind of central mass was huge. It was not expected. and it totally changed everyone's thoughts. Okay, an alpha particle was being emitted by elements as they naturally decay. So naturally, radioactive elements give off particles from their nucleus. So this was a pretty huge particle, too. It's actually an alpha particle, I think it's it's 2 protons and 2 neutrons. It's a helium atom, essentially. It's pretty big. Okay? And the fact that that thing hit something so massive that it bounced back at you, when he was sending it at a piece of gold sheet that they were able to make almost 1 atom thick. Okay, so it was hitting something so massive that it actually like shot back at them. That was crazy. Okay? And then the idea that there was nothing in the majority of the atom. That was crazy too. Again, with Thomson's model, there was something there and it was slightly charged. There just wasn't enough there to stop a huge atom from getting through, right? The alpha particle is really big. But it could travel through this empty space. That idea that there's nothing. Again, you're made of atoms. The idea that most of you is nothing, right? Your nuclei and then nothing, and then electrons way on the outside. It's pretty revolutionary. It's pretty incredible. And we have the electron, we have the nucleus. They talked about the proton in the video. Rutherford, they talked about the neutron. Never mind. Proton, Eugene Goldstein was doing cathode ray tubes similar to Thomson, and he found that he actually discovered a particle moving in the opposite direction of Thomson's particle that still bent, so it was still charged, still bent with the use of magnet, but it bent in the opposite direction. So he was able to discover it was an oppositely charged particle and much more massive. Okay? So it's usually, we say like Eugene Goldstein kind of discovered the proton, but it turned out Rutherford was doing the same thing. Okay? When it said in the video, he just shot radioactive particles at stuff. That's what he did for fun, you know. When he shot them at nitrogen gas, he actually saw hydrogen ions being expelled. And a hydrogen ion, since a hydrogen atom is just a proton and an electron, when it loses the electron, it's just a proton. And he was able to actually see that and measure that, but he didn't publish any papers on it. So these 2 experiments basically led to our understanding of the proton. Then the video talked about James Chadwick working with Rutherford on the neutron. Again, shooting stuff at random things, they were able to discover the neutron, not charged, same mass as the proton, that it was there in the nucleus. So Rutherford, you think about it, nucleus, empty space, proton, and neutron all under his tutelage. He is our atomic model. He did it. He's pretty incredible. Going on further, I told you that everything else beyond the basic structure of the atom has been about the electron. Okay? Rutherford did not do the electron. He really did the core, the nucleus. Niels Bohr, who was working kind of around the same time as Rutherford, was experimenting with light and energy, and he found when he energized elements, they gave off light. Okay? And they were able to quantify that, and they also found that light was only given off at certain colors, like hydrogen, when excited, only gave off red and yellow, never blue or purple, no matter what you did. So he was able to eventually say that every atom had its own unique set of colors that were emitted, and based on that, the idea that somehow there's only specific energies that an atom can have. We're going to talk about light and energy later. All I want you to know right now is that Bohr basically took the Rutherford model with the nucleus and put the electrons in concentric circles emitting from the nucleus, right? Kind of like the solar system model is what it's called. Schrodinger is then our most current model. The solar system model is wrong. Your eighth grade teachers lied to you. Electrons are not moving in concentric circles around the nucleus. Physics-wise, it's physically impossible to keep an electron circling the nucleus at a concentric orbit. Schrodinger did not do any experimenting. Okay, he was working with math, and basically he found a mathematical formula and a mathematical model that fit the atom and was able to predict where an electron was probably at any given time. Based on that, then we've come up with orbitals, which are actual physical shapes of where an electron probably resides, because they don't reside in concentric circles. Okay, they reside in what we call orbitals instead. Again, we're going to do a lot more with Bohr and Schrodinger in a few days. All I want you to understand is that Bohr took the electron and put them into the solar system model, which is concentric circles, because he was messing with light. Schrodinger did not do any experimenting. He was working with math, and instead of putting the electrons in orbits, we now have them in orbitals, and an orbital is a probable location where an electron resides.